Okay, next up we've got Akira Suda who's going to be talking about lazy distribution of container images.
Hi, I'm Akira Suda from NTT Corporation. I'm a manager of Continuity and Mobi and Mobility. In this talk, I will show how to run containers without waiting for completion of downloading the images. And there are lots of alternative image formats proposed to support this lazy distribution technology. And amongst these formats, Stargaze is getting wide adoption, and it's already adopted by Continuity and also FOSDEM. Let's start with the demo. In this demo, I will show lazy distribution of docker.io/library/python 3.7 image. So the top pane is for legacy, and the bottom is for Stargaze. And in this demo, I'm showing Python with .c print hello world. And the Stargaze image just took 5.2 seconds for downloading image and executing print hello world. But legacy format takes more time. It's still taking time. So it took 26.5 seconds. So the Stargaze format is 5 times faster compared to the legacy format for printing hello world. So let's look into the problems of the current Docker and Austria image format. Most of container implementations, including Docker, Mobi, FOSDEM, and Continuity, and client and even Singularity conforms to OCI standard format. The OCI standard is based on the legacy Docker image format. So the Docker and OCI focus on the legacy compatibility rather than making technical innovations. So the biggest problem is that it's based on TAR format appeared in 1970s, originally for magnetic tape media. The magnetic tape media is shown here. That for white circles tape media. This is a PDP-11 mini computer. So the tape archive doesn't support random access for the obvious reason. So this is not good fit for file system images. So the typical TAR archive is composed like this. So you have metadata for the first file at the beginning of the archive, and the second file follows. So to mount this archive as a file system, you need to scan the full virtual magnetic tape. If we could have an external index file, we can mount this as a file system. But this doesn't work for a compressed archive because ZZip doesn't support seek operation. And the second problem is that Tarball doesn't support data purification. So the content registry may contain very similar but slightly different images with different versions, or with different CPU architectures, or with different configuration files and source etc. So the tarballs of this image are very likely to waste the storage. But this is not a huge deal when you have enough budget for the cloud storage that is used as the backend of the registry. So the most important issue is that the tarball requires scanning the whole virtual magnetic tape for mounting the archive as a file system. So in this talk, I focus this issue for the lazy distribution. So why do we want lazy distribution? There's already a good scientific paper about this. So according to this paper, only 6.4% of the data is actually used, and more than 90% just waste for the actual workload. Here are some expected use cases of lazy distribution. So the lazy distribution is the most good for SDK images used in Docker file. So the SDK used images in the Docker file contains some compilers and some libraries and some header files, but most of these headers and libraries are not actually used for actual compilation. And also for Docker files, we don't need to consider fault tolerance against registry failures because Docker build is already flaky. So apt-get install some package often fails with some HTTP errors. So you don't need to consider fault tolerance of the registry failures. There's also good use cases such as function as a service, because for function as a service, the startup latency is really important. And we can also use the lazy distribution for web applications with a huge number of HTML files and graphic files. And it's also good for Jupyter notebooks with big data samples. And also we can use that for GNOME KDE desktop in a container. So maybe just with the era of containerized Linux desktop. But for these use cases, probably we need to consider fault tolerance until the image is 100% cached locally. You can use Kubernetes readiness proof for inspecting the cache status. So 3 years ago, we did first attempt, but it failed. So I will show you the post-mortem story. So our first attempt was that file grain, which I show in Open Source Summit in North America. It was composed of protobuffer index file and content addressable small blob files like this. So this protobuffer message contains SHA-256 digest for each of files, and each of files are content addressable by the SHA-256 digest. But this file grain format didn't become popular because of incompatibility with legacy tarball. And there was also a chicken and egg issue, so it's hard to finalize the spec when no implementation exists. And it's also harder to promote implementation when the spec is not finalized. And also, we didn't clarify the use case, so we too much focused on deduplication, but deduplication appeared not so important. And there was also a huge performance overhead because of the number of small HTTP requests. So the new solution in this year is Stargaze. The Stargaze format is proposed by Brad Fitzpatrick at Google, mostly for accelerating the CI of the Go language project. And it doesn't focus on data deprecation. It only focuses on a lazy distribution. The Stargaze format is fully compatible with legacy tarball format, but slightly different. So in the legacy tar format, the entire archive is gzip, but for Stargaze, each of file is gzip, so the compression granularity is different. And also we have stargaze.index.json at the end of the archive. This index.json has all metadata for the all files in the archive. So we only need this stargaze.index.json for mounting this image. And actual files in the archive can be fetched on demand using HTTP range requests. And the Stargaze is being adopted by several container runtimes, including Containerd and Portman. For Containerd, my colleague Kohei Tokunaga at NTT implemented this as a Containerd snapshotter plugin. And Containerd implementation has more aggressive optimization. For Portman, Giuseppe Scribano at Red Hat is working on fuse overlay with plugin for supporting Stargaze in Portman. And for Containerd implementation, we have some optimization technology. So we profile actual file access patterns by running an equivalent of Docker run. And we reload the file entries in the archive so that relevant files can be prefetched in a single HTTP request. So in this example, we have /app.py as the entry point. So apparently we need this Python file, so we put this file at the head of the archive. And we also need a Python interpreter, user/bin/python3. And this Python interpreter requires /lib/libc.throw. And also we need some Python modules, say user/lib/python3/ blah 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 /foo. But we don't need all Python archive. So we only prefetch Python modules that we really need for app.py. And we prefetch these red files in a single HTTP request. Currently, we need to do equivalent of Docker run for getting file access patterns. But in future, maybe we can do some static analysis using LDD command or maybe some machine learning technology. And here are some benchmark results using Docker Hub. And the continuity host was located on EC2 Oregon region. And for benchmark, we used typical base images with compile hello world workload. So for the Python, the legacy image took more than 26 seconds, and strategies image just need about 5 seconds, so it's 5 times faster. The result was similar for ZCC image. Also, the result was similar for Golang image. For Glassfish image, the result was slightly different. So the legacy image took about 25 seconds, but the circuits without optimization is not so fast. But with optimization, the Stargaze image becomes much faster. So it's about 12 seconds. So it's 2 times faster compared to the legacy format. And we are planning to do much more optimizations soon. For implementation, we are planning to parallelize HTTP operations across image layers. This was hard because of the design gap in continuity plugin design, but I think we can improve in the coming weeks. And for specifications, we are planning to use ZSTD compression format instead of ZZip. This was proposed by Giuseppe for mostly for images with a lot of small files. So using ZSTD is not compatible with the current OCI image spec version 1.0.1. But next revision of OCI image spec is likely to support ZSTD as a compression format. So this is compatible with the next version of the OCI image spec. And we are also planning to integrate strategies into build kit. And we plan to support processing strategies images using build kit. And also we will support consuming strategies images as base images of Docker files that appears in from instructions of Docker files. And also there are other alternative formats that support lazy distribution. For example, CERN FS is already widely deployed in CERN and their friends' environments. But the CERN FS format is not compatible with legacy OCI tables. And there's already implementation for continuity. And there's also a proposal of what is called OCI version 2. This is proposed by Alexa Sarai at SUSE, but this is not an official OCI format at this moment. And it's also not compatible with OCI version 1 tables. The OCI version 2 will focus on data purification using a RESTIC algorithm. So it's very different from Stargaze format. And there's already work in progress implementation for Umochi image manipulation tool. But as far as I know, there is no runtime implementation exists for this OCR version 2. And there is also IPSCS proposed by Edgar Lee at Netflix. The IPSCS format is built on IPFS, which is P2P storage. This is not compatible with OCI tables, but we already have implementation for ContinuD. And also, Microsoft Azure built something similar using assembly protocol and VGD images, but this project is not free software at this moment. So to recap my talk, there are lots of alternative image formats proposed for RESI distribution, but compatibility is very important, and Stargaze is getting wide adoption. It's compatible with legacy OCI images, and it's already adopted by ContinuD and also by FOSDEM. And for ContinuD implementation, we support prefetching optimization. So our implementation is available at this GitHub repo. This is currently under my colleague's GitHub account, but this is expected to be moved under github.com/ContinuD soon. And we request for comments such as valid and invalid use cases, and how we can do more efficient optimization. Thanks.
Questions?
Hi, thank you for the talk. Do I understand correctly that only the needed files will be downloaded?
Sorry, just speak louder.
Do I understand correctly that only the needed files will be downloaded, so not the full image will be downloaded on the...
Yeah, so not full images are downloaded. Only files that actually accessed is downloaded.
Okay, cool.
Other questions? Up. Oh, no. Oh.
I didn't understand if it is already integrated with build kit or not.
So not integrated into build kit. We are planning, so please stay tuned. Please wait.
Oh, yeah.
So who creates the Stargaze index JSON file, and how many container images on any given...
Sorry, JSON what?
The Stargaze JSON index file. Who creates that? The build kit tool?
Currently, we have some converter tool in our repository. So please see github.com/ktalk/stargaze/snapshotter. We have some converter command in this repo.
So when you say wide adoption, I just want to know percentage of images that have the Stargaze JSON file already today.
So the JSON file is generated by the converter tool in this repo. Does that answer your question?
And last question, any distribution spec changes that you expect for this to have wide adoption?
No change.
Okay.
So it's even compatible with Docker Hub. So actually, we use Docker Hub hosted by Docker Inc. Without any modification.
One last question, if there's any. I think we're good. Thank you.